So now, in a previous video, we looked at this circuit here. So what we're simulating is if we're powering this with an 8.4 volt battery, which is a couple of series lithium ion cells that are fully charged right there. As they discharge, their voltage goes down, and before they completely discharge, I would like to turn this load off there because you don't want to over discharge lithium ion batteries. So that was the motivation for the circuit. It's not the best way to do this, to cut power from a battery when its voltage gets low enough, but it will work, decently well, as we'll see. So power supply voltage is 8.4 volts. I figured we would focus on using the multimeter to test things out when it comes to this circuit. So this is an auto ranging meter. All I have to do is set V for voltage, and I have these kind of crossed over because I got black over there. But I don't have to move the red probe for anything other than high current right there. And it's auto ranging. Just have to set it to V. If there's numbers, set it to a number higher than you can expect to measure, especially when it's current. You never want to measure more current than what the meter is set to measure. But we're not going to worry about that too much. First, we're going to look at the supply rail voltage. It's going to be lower than what the power supply says because we lose a bit in connections and stuff. Plus, the power supply might not be as accurate. So I got these alligator clips. I just crimped them just with pliers to the ends of breadboard jumpers right there. And these seem to make a pretty good connection. And there you can see we're losing a little bit of supply voltage along the way. That's one thing to expect. But first thing we should look at is we have our load. So that's the bulk of the current you see on the screen. There is some other current. We got the Zener diode. Current has to go through it to build up its Zener voltage and so on. But its Zener voltage is low enough where we got enough voltage difference across the emitter and base to get the transistor to probably be on fully. The best way to check is to go across the load, and we should have about the full supply voltage across the load, and it's actually a bit lower than I expected right there. Oh, because I'm off a spot. That's the resistor. There we go. Now we're at the collector, and so again, we're not getting the full supply voltage to the circuit. The transistor is dropping a little bit of voltage. It's not a perfect conductor, but out of that 8.4 volts, we got 8.18 across the load, basically all of it for the most part. And again, transistor is not a perfect conductor, and we can look at the voltage across the transistor by going to the positive supply right there, because that's going up to the emitter, and then putting the negative over here. And so yeah, transistor is dropping about 0.08 volts right there. So in any case, that's to be expected. Again, it's not a perfect conductor, but it's close enough for a load like this. It's basically no difference what voltage the transistor is allowing across the load versus the supply rail. There is a little bit of loss, but not much. Now we go to the base of the transistor. We are trying to set 5.6 volts across there. We got the positive supply from that resistor to the Zener diode, and when the Zener diode, it doesn't conduct current. It's a 5.6 volt Zener diode. Again, that's not perfect either, but it doesn't start conducting until you get 5.6 volts. What that accomplishes that you limit 5.6 volts across the Zener diode. So we can look at that over there, and I actually did this measurement a little bit earlier, and it was doing 5.6 volts, a little bit better than this. But again, this is still close to 5.6 volts. If I lower the supply voltage, you'll see that it does go down a little bit. It's not a perfect voltage regulator. Now, I actually didn't demonstrate this yet. If I lower the supply voltage enough, then the LED turns off. So it should be somewhere around 6.2 volts because we got the 5.6 volts of the Zener diode, and the emitter to base drops about 0.6 volts. But if it gets below that, then there is no, when that's the emitter to base voltage, if it gets below about 0.6 volts approximately, then it doesn't conduct anymore. And without emitter to base current, there can be no emitter to collector current because we're working with PNP right there. And so we got not enough current to maintain the voltage across the Zener diode, plus the voltage you need through that resistor right there, actually going in that direction, to get current to flow. That's the main thing. So yeah, we can come back to the base right there, and it looks like the meter is actually somehow given enough of a signal to get it to turn on. That's because we got that to the negative supply. So that's something you got to be aware of, be careful of. Yeah, even if I go to the negative there, that's enough to give it some of a signal. But there you can see we're below about 0.6 volts when it comes from the emitter now, positive supply, to the base over there. And if we go to 6 volts, it went down even more right there. So we should have pretty much cut off all current from the load, or all voltage, and thus all current, which is the main goal. By the time I got to 6 volts with the battery, I wanted the load off completely. It doesn't completely remove all the current that the battery would have to provide, but it is pretty close. And yeah, we got a weird negative voltage just because you know, it's like stray signals or something. That's not really voltage across the load. The voltage across the load too, you need about 2 volts across the resistor just to get it to conduct, at least about 1.5. That's something else to be aware of. So we may not have cut it off completely, but main thing is there's no voltage difference across the resistor, practically none. So it's not conducting current right there. So again, these are all things to look for. We can remove the LED and see if the voltage reading we got was just kind of like a capacitive effect or something. There's all kinds of things where it's not the actual like power voltage. There may be like stray signals that somehow get across there. We can go up to the resistor right there and see without the LED we don't have a voltage right there. We are at the collector, and just to make sure we didn't like miswire something, I can go up to 7 volts, and now we got almost a full 7 volts across there, 8 volts. I shouldn't go much higher than that. It's 470 ohms. We don't have the red LED dropping a couple volts. But there we go, 6 volts, no voltage difference across the resistor. Of course, the Zener diode, 5.6 volt Zener diode, we're still above that, so there's going to be some leakage current through there. But we need an additional 0.6 volts or more, approximate, these are not exact numbers, across the emitter and base, because it's like a diode, like a regular rectifier diode with a forward voltage of about 0.6 volts. Again, it's not exact, and you know, builds up a little bit more at higher currents and so on. And then we got to overcome the resistance there to get the current flowing, and that's why you need that resistor. If you just have the diode drop there and the Zener drop, once you get a high enough voltage, it's basically a short circuit above that voltage. So you need a resistor to limit current, but don't have to be terribly high or terribly low. So we got that right there. But anyways, we did successfully see that if we get a low enough voltage, there's no voltage across the load, although the LED kind of makes it a little confusing. It build up like a stray voltage or something, and since the multimeter doesn't really let current flow through, just a very small trickle, you know, it can get read a voltage even though that voltage isn't providing power. There's no current flow. So just something to be aware of. You always gotta try to understand. There we go. We got that stray built up voltage again from something. Probably just a very tiny amount of leakage current allows to build up across there, but it's practically no current as far as the battery is concerned, although we do have some right there. So again, this is not a perfect battery protector, but far better than having no transistor cutting off the load. This load would still be really well lit up at 6 volts right there, whereas now we cut it off. So that's going to save a battery a lot more than no protection at all right there. So that's the main lesson. But in any case, hopefully that wasn't too confusing. and I hope you enjoyed. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.